Our universe seems to play by a set of rules. We're only just starting to figure them out, but from the tiniest particles to the most massive galaxies, everything appears to follow a predictable cosmic dance. The laws of physics tell us that on the absolute largest scales, the universe should be pretty much the same everywhere. A balanced and consistent tapestry of matter and energy expanding smoothly in all directions. But what if it isn't? What if there are hints that this tidy picture is wrong? What if something, somewhere out there, is breaking the rules? Because at the very edge of our vision, something strange appears to be pulling on the universe. This isn't just one galaxy or a single star. It's a controversial claim about entire clusters of galaxies, supposedly streaming in the same direction at over 2 million miles per hour. Some scientists dubbed it the dark flow. It was a claim that our corner of the cosmos was being dragged towards an unknown destination, somewhere beyond the edge of the observable universe. The problem? According to our best models of the cosmos, this shouldn't be happening. So, what was this massive, unseen force that was supposedly hiding in the dark, and what could it mean for our place in the universe? To understand this mystery, we have to look back to the very beginning. Our key to spotting this anomaly lies in the oldest light in the cosmos, the cosmic microwave background, or CMB. Think of the CMB as the universe's baby picture. It's the faint, fading afterglow of the Big Bang, a snapshot of the cosmos when it was just 380,000 years old. This ancient light fills all of space, and it's remarkably uniform. For cosmologists, it's the ultimate reference point. Relative to it, the motions of galaxies should be more or less random. And for decades, that idea held up. But in 2008, a team of astronomers led by Alexander Kashlinsky decided to look closer. They used data from the Wilkinson Microwave Anisotropy Probe, or WMAP, a satellite that had just created the most detailed map of the CMB. But they didn't look at the CMB directly. Instead, they studied how its light was subtly changed as it passed through hundreds of massive galaxy clusters. Here's where the idea gets really clever. As CMB photons travel through a galaxy cluster, they bump into hot gas trapped inside. If that cluster is moving, it gives the photons a tiny push or pull, slightly changing their temperature. This is known as the kinematic Sunyaev-Zeldovich effect, or KSZ effect. It's an incredibly faint signal, so faint that it's impossible to see from a single cluster. But Kashlinsky's team figured that by combining data from hundreds of clusters, they could average out the random noise and see if there was a collective underlying motion. They studied a catalog of around 700 clusters, expecting to find random movement. Instead, they found the opposite. They claimed a huge number of them were moving together in a coherent stream toward a patch of sky between the constellations of Centaurus and Vela. They had found what they believed was evidence for a bulk flow stretching across billions of light years, moving at a staggering 600 to 1,000 kilometers per second. The name that stuck? The dark flow. This was a deeply unsettling claim. It seemed to fly in the face of the cosmological principle, a fundamental idea that says on the largest scales, the universe is basically the same everywhere you look. The distribution of matter should be even, and the expansion of space should be uniform. A smooth, random distribution of galaxy clusters is what this model predicts. But the dark flow claim suggested something else, that the universe might have a preferred direction, a giant cosmic arrow pointing towards something unknown. The gravitational pull of all the galaxies and clusters we can see isn't strong enough to create such a powerful, unified current across such a vast distance. This left scientists with a profound and disturbing possibility. If the pull wasn't coming from inside our observable universe, it had to be coming from outside of it. The observable universe is simply the sphere of space where light has had enough time to reach us since the Big Bang. It's our cosmic window. The dark flow hypothesis suggested that something massive and ancient was lurking just beyond that horizon, its gravity reaching across space-time to tug on our reality. The claim was met with both excitement and a heavy dose of skepticism. If confirmed, it could rewrite our most basic understanding of the cosmos. It was a crack in the standard model of cosmology, a model that had been wildly successful. And like any discovery that challenges the foundations of science, it immediately came under intense scrutiny. This is the kind of mystery that pushes science to its absolute limits. We're talking about forces that might defy our models and structures that could lie beyond our vision. If you find these cosmic puzzles as fascinating as I do, consider subscribing. We explore these mind-bending topics every week, and your support helps us ask the biggest questions there are. So, what could possibly be powerful enough to pull on hundreds of galaxy clusters from beyond the edge of the visible universe? The theories ranged from the plausible to the wildly speculative. One of the more out-there ideas was that the dark flow could be the gravitational signature of a colossal structure that existed before cosmic inflation, a moment of hyper-rapid expansion right after the Big Bang. Perhaps this event stretched the universe so much that it pushed ancient structures far beyond our cosmic horizon, leaving only their ghostly gravitational pull behind. Other, even more exotic theories wondered if this could be evidence of another universe leaking gravity into our own. It's a tantalizing thought, but one without any direct evidence. But the most important part of the investigation wasn't just dreaming up theories, it was checking the data. The scientific community got to work. The KSZ effect is notoriously difficult to measure, and many cosmologists worried the signal was just a statistical fluke or an error in the incredibly complex analysis. The real test came with the European Space Agency's Planck satellite. Planck was WMAP's successor, designed to map the CMB with far greater precision. When the Planck team first analyzed their data in 2013, they reported that they found no evidence for the dark flow claim. To many, that felt like the end of the story. The anomaly was an illusion, a ghost in the WMAP data. However, the debate didn't die instantly. In 2015, members of the original team reanalyzed the public Planck data using their own methods and argued that it was consistent with their earlier findings. They suggested that since the two satellites had different instruments and potential errors, finding a similar signal in both could actually strengthen the case. Still, since then, the consensus in the broader scientific community is that the evidence for the dark flow is inconclusive at best, and most analyses find no such effect. The debate has largely faded, but the mystery of large-scale cosmic motion itself has not gone away. In fact, it has become part of a larger pattern of puzzling features seen at the edges of our universe. The dark flow isn't the only anomaly lurking in the cosmic microwave background. When astronomers study the CMB, they find other strange features that don't quite fit the standard model. There's the so-called axis of evil, a strange alignment of the largest patterns in the CMB with our own solar system. There are odd temperature imbalances, where one half of the universe looks slightly different from the other. And most famously, there's the CMB cold spot, a vast region of space that's unusually chilly. Some have speculated this could be the imprint of a gigantic supervoid, though recent studies suggest a void alone can't fully explain it. These anomalies, including the contested dark flow, are not definitive proof of new physics. They are faint signals hovering at the edge of statistical significance. They could be incredibly rare flukes, tricks of our instruments, or noise from nearby galaxies that we haven't perfectly filtered out. But they refuse to go away completely, and that's why they matter. Science doesn't just advance by confirming what we already think we know. It leaps forward when we find things that don't fit, when we're faced with an anomaly that whispers, "Your theory is incomplete." Whether the dark flow claim was real or not, the search for it has pushed our technology and our understanding forward. It forced us to develop new ways to hunt for the subtle motions of galaxies across billions of light years. It serves as a powerful reminder that our map of the universe is still a work in progress. We're on a tiny island of knowledge, surrounded by a vast ocean of mystery. The observable universe is just that, what is observable to us right now. It is not the whole of reality. These anomalies are like faint lights glimpsed across that dark ocean. They are hints that there is more out there, a grander structure, a deeper set of rules we have yet to discover. They are the breadcrumbs that might just lead us to the next great revolution in cosmology. So, is our universe being pulled toward its doom by some unseen force? Probably not. But the story of the dark flow reveals a more profound truth. It shows us a universe that is still packed with surprises, a cosmos far more complex and mysterious than our neat models suggest. The controversy and the debate aren't signs of failure. They are signs of science working as it should. A relentless, passionate quest to understand our place in the grand scheme of things. And it leaves us with the most exciting question of all. What else is hiding out there, just beyond the horizon, waiting to be discovered?